So far we have discussed MM1 queue. Okay. Now, we are in the position to launch towards a means trunk switch analysis things which are actually known as Erlang formulas. So, we will try to see some more complicated system, Markovian system, and then try to see how they are linked to trunk switching. Okay. So, that is what we will be doing in this class. Let us try to see. So, what we will do, we will now try another system where we have a queue and we have now multiple servers, not single server. Okay. What happens? There is a queuing place, customers arrive, of course, a Poisson arrival. So, Markovian arrival with parameter lambda. They have service time, all servers are identical. So, basically they do not, every customer whichever server it goes, they are identically treated and they get actually a service time which is independently and identically distributed, exponentially distributed, and its parameter is mu. That means 1 by mu is the average service time. So, this is something we know. So, this is the system now we wish to analyze. Okay. So, this kind of system we want to analyze. Now, let us try to first see why this system is identical to trunk switching. So, let us try to understand what happens in trunk switching. So, trunk switch, if you remember, we had let us say multiple lines, okay, 1, 2, 3 up to m, and there are multiple inputs. Okay. So, over here it might be finite input, we can also assume that it is actually too many inputs. So, it is almost infinite input. So, that should be our assumption. Okay. Otherwise, it will be a finite customer. So, we can do the same analysis with finite customer. So, that is a different kind of analysis that we will have to do. But right now the assumption will be that probably local subscriber, too many customers are getting connected. Okay. So, that is almost infinite, okay. And their aggregated arrival rate is lambda. Okay. So, and they are Poisson because independently they are making arrival. So, they are independent to each other and it makes a Poisson arrival. Okay. So, arrival means call arrival. So, somebody is requesting call. So, some customers is requesting call, some customer is requesting call. At a time every customer requests a call, you give a server just like over here. Okay. Only thing is that as if the queue is not present. Okay. So, we can also think about that queue is not present, that means buffering place is 0, that we can assume, but we can also have some buffering place, that might be also true. So, buffering place is there means it is like this. Earlier days if you used to call, then they used to say that all lines in this route are busy and please wait. You can actually means wait over there, whenever the next connection will be free, or that means the next trunk server is free, it will connect you. And all the customers, there might be multiple customer like that, you are waiting over your telephone, there might be multiple customers who are waiting. So, that is actually queuing place, everybody is waiting. Whenever they means, and whenever they are waiting, they also keep a record that who has come first, who has come second. So, that is how virtually they create a queue. Okay. So, you are waiting, there might be some other guys also who has taken their telephone, started ringing, they are waiting, but basically the system knows when you started. So, they know those starting time, accordingly they have arranged the queue, and then whenever the trunk switch one of them is free, that means one of the customer who is already talking has disconnected the phone. So, immediately the server becomes free. So, suppose all these are occupied already, now suddenly whomever you have given the second connection, he has disconnected it, that means this has now become available. Whenever it is available, the first one standing in the queue or first one who has arrived, who are waiting, that will be given the server. So, it is completely a queuing system, as you can see. They are making Poisson arrival. If the servers are there, they are giving the server. How much time they are taking for service? The call duration, which is 1 by mu, which is exponentially distributed, no problem with that. all customers are equivalent, that is also true. Okay. So, equivalent customers, because they will be all making voice calls, they are equivalent kind of customers, we can assume that way. Okay. So, if they are equivalent kind of customers, and then all servers are equivalent because they give one connectivity, one telephony connectivity of 64 kbps or TDM connections. So, if this is the case, then it is actually a these kind of multi-server system. Okay. So, all we have to now do is analyze these kind of multi-server system. So, in this multi-server system, it might be two scenarios might occur. So, in one scenario you might be waiting. So, whenever you are basically all servers are busy, this particular thing you hear, immediately your call might be dropped. That means, you try to make connection because all servers are busy, all trunks are busy. So, your call is dropped. So, this is called block called cleared. So, you have been blocked because all the servers are busy. So, your call has been cleared. So, that scenario is called So, associated system, what that system will be? System will have no queuing place. So, it will just have server, everybody arrives, occupies a server. If all servers are occupied, there is no place for keeping them in queue. So, they will be blocked. So, associated system, if you see, that will be Markovian arrival of course, Markovian service of course, how many servers are there, m number of servers are there, and how many total place is there, only m server, no queuing place. So, this is also m. So, this is called MMMQ. Of course, the last column is infinite because you have already assumed that infinite customer base or infinite population is potentially or they can potentially make arrivals. So, this is that system and it is generally being characterized by Erlang B model. We will see that. Okay, what is Erlang B model? And the other scenario where you might be waiting in a queue. So, that is called block call delayed. What does that means? That means, if you are blocked, if all servers are occupied, then you can wait in the queue, whenever next server will be free, you will be given connectivity. That means, you will have to now wait. So, there is a waiting time. Okay. And what will be the waiting time? That depends on the kind of calls that are going on and all those things, all kinds of system parameter, all kinds of arrival characteristics. So, everything will determine what kind of waiting or waiting statistics that will be happening, average waiting time that will be happening. So, those are the things we will have to analyze. So, in block call delayed system, what is the system? Associated system. So, you have Markovian arrival again, Markovian service, m number of servers, but after that I do not have to specify anything because there are infinite place for waiting. As many customers are there, we have already said infinite number of customers, they all can potentially wait. They can all make calls, only m of them will be occupied, means m of them will be given connections, all other rest can be waiting. So, therefore, the waiting place can be infinite. So, therefore, the number of customers that system can hold, that also goes to infinity. So, I can just say MMMQ, rest of the things are infinite, and this corresponding formula is called the Erlang C model or Erlang C formula. Okay. These are the two systems that now we will be interested in analyzing. Okay. So, these two systems will be now trying to analyze. So, let us first try with this one MMM system. Let us try to see how do I characterize the Markov chain, associated Markov chain, because if I can construct the Markov chain, if I can see the transition rate transition matrix, then rest of the things are done. We just have to solve some set of linear equation like we did for MM1Q. So, that is all we will have to do if we have to do it. Okay. So, let us see MMMQ, this Erlang C model or block call delayed, where you can actually wait. So, for that, how do I construct the model? Because it is Markovian arrival and Markovian service. So, basically the state description nothing changes. How many customers are there? There will be always again some integer number of customers and nothing else is required. So, Markov state will be similar 0, 1, 2, 3, it just counts how many customers are there in the system. Okay. M minus 1, m, m plus 1 and so on, it just goes up to infinity. This is also because I have infinite buffer. So, it also goes up to infinity, it is not finite thing. Now, let us try to see the rate matrix, okay, or the transition rate. Over here arrival is happening with parameter lambda. So, lambda is the arrival rate. From 0 it will be arrival rate. If there are 0 customers, that means nobody is there, no circuit has been created. So, nobody is present in the trunk switch. So, therefore, the first customer arrives with arrival rate lambda. From 1, what will be the arrival rate of next customer? That also is lambda, because with lambda arrival rate only the arrival happens, irrespective of how many customers are there inside the system, because there are infinite customer base outside. From there 1 or 2 customer you take inside, it does not matter, there are still infinite number of customer base, they will be again still populating with rate lambda only. So, it happens to be all lambda. What changes is over here. If there are one server, let us try to now understand the situation from with a time diagram. Let us take just 2 server. Okay. So, what is happening? The first customer arrives, he goes into this. Okay. The second customer arrives, he also goes into second server, because whenever the server is free, customer will be given the server. Okay. Only the third customer arrives, he waits over here. Okay. So, timeline if I see, I have server 1, I have server 2 and this is the queue. First customer arrives, he immediately goes to server 1 and gets his service. This is the service time probably. The second customer arrives, so this goes into server 1. Second customer goes, because server 1 is busy, so he can go to server 2. Now, if the third customer arrives, so for him both the server at this instance are busy. So, therefore, he has to wait. While waiting, now let us try to see how many systems are there in this, how many customers are there in the system. So, overall 1, 2, 3 customers are there, both the servers are occupied. Now, when he will be actually going into service, whenever one departure is happening, either this departure or that departure, whoever is earlier. So, how do I say when the departure will be happening? That is the rate with which one departure will be happening, that means the state will be coming down. So, how do I characterize what is the departure rate? So, over here there is an exponential distribution with parameter mu. We know that this residual time. So, he has arrived over here, from there he will be counting, this is again exponentially distributed with parameter mu. This is also exponentially distributed with parameter mu. So, it is actually minima of 2 exponential distribution with parameter mu, okay, both the one has having parameter mu. So, therefore, the minima of this distribution we have already characterized it, it will be addition of those 2. If there are 3, then it will be addition of those 3. So, therefore, the rate will be mu plus mu, it will be 2 mu. If there are 3, it will be mu plus mu plus mu, 3 mu. So, now let us try to see when there is one server busy. So, 1 means what? One server is occupied. So, what will be the corresponding rate? It will be mu. Over here when he is in state 2, how many servers are busy now? 2 server is busy, because he is in 2 state means state 2, there are m server, he is in state 2 means 2 servers should be busy. So, what should be the departure or departure rate or rate of going out from the system? That should be now associated with 2 mu, because 2 servers are occupied. Over here it should be 3 mu and so on. So, basically even if this customer does not come, if from the observer point of view at this time instance I try to see what will be the rate of departure. So, right now 2 customers are there. So, my state is 2. So, from 2 when it will become 1. So, that is what I am trying to account over here. From 2 it will go to 1, that means one of them will be departing. What is the associated rate? So, that is minima of these two exponential distribution. So, that should be 2 mu. If there are 3 server and 3 are occupied, then minima of 3 exponential distribution, that is associated with 3 mu. From this time instance, so suppose I am observing what is the possibility that one arrival will be happening before a departure. So, basically that is coming with lambda. So, that is why it is going with lambda. So, with lambda rate it is actually going to upper state, and with 2 mu or 3 mu depending on where he is coming down. So, now everywhere let us say if it is 4, then also it will be 4 mu, because there are 4 server. Up to m this will be happening, this will be continuing m mu. When it goes to m plus 1, what happens? Let us try to understand that scenario. That was the scenario I was depicting over here. So, there are 2 server already occupied, third customer has come. For him, how do I now? So, third customer has come already with lambda rate. So, it has gone to state probably 3, but from there I now try to see what is the departure rate. So, at that point only for 2 server I will be accounting. So, therefore, at m plus 1 also only m server I will have to account, because m server is busy, m into mu rate I can see that one server will become free. So, therefore, this will still remain m mu, and all the higher one will still remain m mu, because there are only m number of server. At max with m mu rate he can serve. So, therefore, the departure rate will be at max m mu when all m are occupied. So, all the state from m onwards all m server must be occupied, because if m plus 1, 1 must be in queue, all m servers are occupied, m plus 2, 2 must be in queue, and all m servers are occupied. So, therefore, all these places service rate will be m mu, only from here onwards it will be reduced. So, as you can see with this simple description of understanding of the queuing, we can actually construct this whole Markov chain. Now, once I have constructed this Markov chain, now I just have to write down all the equation, governing equation, and then solve them recursively. Whenever I solve, I get my whatever things I want to characterize. So, over here I am interested in this, that what is my blocking probability, because overall blocking probability or probability that I will be delayed. So, that probability I want to calculate. Let us try to see how do I, that is the L&C formula actually, how do I characterize it. So, what is the probability that I will be delayed? If I am in state m, means I am a arriving customer, if I see the system in state m like this third customer. So, there were 2 server already occupied, if I arrive I will be blocked. So, basically if while arriving if I see the system in state m or state as many servers are there, that many state. So, that or more than that, then always I will be blocked. So, all these state probability if I add them, that must be the blocking probability or called delay probability. That is the probability that my arriving customers will be delayed. So, therefore, this pi m plus pi m plus 1 up to infinity, this is my probability that block called will be delayed, or this is actually called the Erlang-C formula. Okay. So, all I have to do is now evaluate this pi i's like we did for MM1Q, and then sum them from m to infinity, and that should give me the overall blocking probability. Okay. So, basically what I can now see that I will get, that should be definitely dependent on the traffic parameter, which is lambda and mu, or I can say lambda by mu, this rho, this will be associated with this, and it will also depend on this value m, the characteristics of my trunk switch, how many trunks I have given this m. What will be happening? I will be getting a blocking probability with respect to this rho and m. Now, m is my design parameter. When I try to design a trunk switch, I have to give how many output links I will be giving, because that is costlier. More number of links I give, I will have more cost. So, what I try to design is some targeted probability of this BCD or block called delayed probability, that call will be delayed. So, that probability for a particular arrival and service rate, I will be designing a M. So, this is my design that we have targeted earlier. In least graph we were targeting this kind of design also, but that was done in a more average analysis. Over here we are actually doing exact analysis. Okay. So, this is very exact analysis because we have developed the whole theory, and this particular probabilities are actually the overall probability that will be happening, that we will see in the, if as long as the Markovian assumptions, all the assumptions that we have taken, that are true. That means lambda is below mu for stability condition, then its Markovian arrival and Markovian service. These two things are happening, and the amount of customers they are coming, they are almost going towards infinity. So, if these assumptions are true, then these formulas are accurate stochastically, and the average value that we will be getting, you will see that in a real system whatever is happening, the average values also will be accounted for. So, let us try to see how do I analyze that. Okay. So, over here I can again do the same thing. So, from this 0 state, if I consider what is the outgoing rate and what is the incoming rate. So, I can write lambda into pi 0 is equal to mu into pi 1. The first equation remains the same, only the second equation changes. Now, what happens? Lambda into pi 1 becomes 2 mu into pi 2 and so on. So, basically the nth one, what will happen? Lambda into pi n minus 1, that should be n minus 1 into mu, oh sorry, n into mu into pi n. Okay. Remember, this happens up to m. So, this keeps on going up to m, this is true. So, over here this is true. So, if I just put it lambda into pi m minus 1 but beyond this the formulas gets changed little bit. Beyond this, if I just put the formula of, as you can see, this will still remain m mu. Earlier this coefficient of mu was increasing, but this is where it gets fixed and so on, it just goes on. So, any lambda into pi I, this will become still m mu into pi I plus 1, something like that. Okay. So, that is the set of equation that is being constructed, and it will keep on growing. Okay. So, now if I just keep substituting, then we will be getting our associated formula. Okay. So, if I just do those things and then write summation this pi I goes 0 to infinity, if we do this summation, that should be 1. I put that, everybody I will be able to represent with respect to pi 0, right. So, from here pi 0 I can solve and put the pi 0 over here, and then I get my solution. So, just I will not do that, you can take that as homework or your assignment will have this. So, all that will be happening. You can see over here pi 1 becomes lambda by mu, that is rho into pi 0, pi 2 happens to be 1 by 2 lambda by mu again into pi 1, or I can write this again, this is rho, another rho. So, basically rho square divided by 1 into 2 by 0. Similarly, if you do, this will be rho to the power n divided by all this 1, 2, 3, 4 factorial will be coming. So, n factorial pi 0. So, this goes on. Okay. Only thing is that from here onwards it will be slightly changed. Okay. So, rho to the power n will be happening, but this will no longer be factorial m. Okay. So, this will not be factorial m, there will be a factorial m part and then this m to the power rest of the things, okay, I minus m, that will be happening. So, you can construct this very nicely, then you write this, then you get a summation term in pi 0, you solve that, you get your all the corresponding pi 1, pi 2, pi 3 every value, and then all you have to do P B C D will be from pi m to infinity, you take the solution, replace it, it will be represented with respect to pi 0 from the normalization equation you will be getting, you substitute that, you get your Erlang C formula, whatever that formula is, you can take that from the textbook, okay, that will be there in your study material also. So, you can derive that formula, this will be also coming in exercise. So, you will be able to do it. So, only thing that is left, let us try to see if I can do the Erlang B formula now. What is that system Erlang C? Only servers are there, m servers are there, 1 to m, nothing else, no queue, all arrival happens, they are just getting distributed to the server. Corresponding Markov state and Markov chain, what will be happening? Now, this has no queuing place. So, it is a m, small m, and how many customers can be total maximum taken in the inside the system? Only small m, because only small m places are there where customers in the server they can be attached to and get service to, no queuing place. So, basically the system is now truncated, the Markov chain is no longer an infinite chain, it goes from 0, the state can go up to m. So, 0, 1, 2 up to m only, that is it, it does not go beyond this. So, it is a finite Markov chain. Arrivals are again lambda accordingly. What is this departure rate? That should be when same logic, if one server is occupied, that should be mu, 2 server occupied 2 mu, m server occupied m mu, that is it, it is as simple as that. This Markov chain I will have to again analyze, again I can put those total outgoing and total incoming rate of probability balanced, I can put those equation, I can solve them similarly and I get my all the state equation. Remember over here the normalization equation will be finite because it has finite state. So, I will go from 0 to m only, pi I that must be 1. So, this normalization equation will be finite normalization, means finite summation will be there. Okay. So, from there you will get relationship, means all these equation you put, you will be getting relationship with respect to pi I to pi 0 and then put it over here, pi 0 will be solved and then you get all the state equation. Now, let us try to see what is the blocking probability. From here, how do I calculate the blocking probability? The blocking probability is very easy over here. As you can see, any other state you are there, if you actually arriving customer comes to any other state, they are not blocked, because if he arrives when 2 servers are occupied, he will just be the customer who will take it to the third server and he will be already getting the clock. So, he means server. So, he is not getting blocked, only when m are occupied. So, whenever the all m servers are occupied, that time only your blocking will be happening. So, this pi m is the blocking probability. So, and that is if you solve this, calculate the probability of mth state, that pi m is your blocking probability and that is called the Erlang B formula. That means block called are now means they are cleared. You do not actually, whenever call is blocked, you do not give them chance, they are cleared, they can do arrival later on next time, but at this time they will just say sorry, okay, all trunks are busy. So, again if your system is like that, you do not allow them to wait, then this is the blocking probability and accordingly you can actually calculate the blocking probability. It will be again related to your m and the rho. So, from the knowledge of rho, because that should be traffic, that should be characterized from the knowledge of rho and a targeted blocking probability, you will be always able to decide m. So, this is famous Erlang B formula, again you can derive it, I am not deriving it, it is just algebraic manipulation. So, we will be giving assignment for that. Okay. So, you can do that and you can always check those formulas, those are available anyway. So, Erlang B and Erlang C formulas, These two formulas are heavily used for trunk designing, and we have seen that how queuing theory can be applied to derive these two equations and further design your trunk switch. So, with this we will end our queuing theory discussion right now. We will go into now, basically this has given us all the analysis of corresponding circuit switch network. Now, we will launch ourselves towards a packet switch network, which has happened, a paradigm shift happened. So, we will see that little bit of initial introduction, how that shift has happened, what was the transient period where this transition was happening. So, those things we will discuss, and then we will again maybe come back theory of queuing and the analysis of that for those packet switch analysis as well later on. Okay, thank you.